In this video tutorial, I will try to explain how to solve the focused questions for the end of term exam of the grade 12 ASP. Define acid and base according to Bronsted-Lowry theory. For Bronsted-Lowry theory, an acid is a proton donor, while a base is a proton acceptor. So I'm going to give an example to this. Here's a Bronsted acid. If I add this acid to water molecule, it's going to be a donor of H+. So we'll get A- plus H3O plus the hydronium ion. So that's why HA is a Bronsted-Lowry acid, because it donated a proton to the water molecule. Now if I have a base, so I'm going to use B as a base, and I'm going to add plus H2O. So a base is a proton acceptor because it accepts an H plus from the water molecule to become BH plus and OH minus. The formation of OH minus in this equation indicates that this is a base, while the formation of H3O plus in this equation indicates that what we have is an acid. Which of the following is a Bronsted-Lowry acid? So again, to be a Bronsted-Lowry acid, it must be a proton donor. So we look here, we see that in this compound, the acetic acid, there's an H plus that can be donated. And also in this one, the hydrofluoric acid and the nitrous acid. So all of these are Bronsted-Lowry acids because all of them, they contain H+. Identify the acid, the base, the conjugate acid, and the conjugate base in each equilibrium in this question. Now you need to know that an acid, when it donates a proton, it becomes a conjugate base, and the base, when it accepts that proton from the acid, it becomes a conjugate acid. Now I can do it in a very quick way, and by simply looking at OH minus here, I understand that this given is a base, and the OH minus is a conjugate base. Why I use the word conjugate? Because it's on the product side. Now if this is a conjugate base, then this one is a conjugate acid that is coming from this base, and since this is a base, then this is an acid. Now I'm going to explain this again in a different way. What if I didn't look at OH minus? What I need to do is I need to check how the H is going between, how the H plus is being transferred between these two species. You note here that we had 2 hydrogens and now they are 3. It means that this H2O took one H plus and gave it to this one. And that's why this H2O now became OH minus, because this was donated. So therefore, H2O being the donor, that's a base, and it turned, that's the acid being the donor, and it turned into a conjugate base. And because this is an acid, then definitely this is the base, which turned into a conjugate acid. Now let's look at another example, and I'll solve it in 2 ways. By simply looking at the equation, we notice here that we obtained an acid. Being on the product side, I'll call it a conjugate acid. Now, if this is a conjugate acid, then definitely this one is a conjugate base coming from an acid. And if this is a conjugate acid, then this one is a base. Now the other way, let's look at how the H plus is being transferred between these two substances. So here we go. We have here 2 hydrogens, and now they became 3. And we had here 7, and now they're just 6. This means that C3H7NO2 is the donor. So that's the acid, and that's the base. And this acid turned into a conjugate base, and this base turned into a conjugate acid. So whenever you get these equations, just look at simple species like OH minus and H3O plus. If you obtain OH minus on the product side, it means it's coming from an acid. And if H2O is behaving as an acid, then definitely it's being added to a base. And if I obtained H3O plus on the product side, then this is a conjugate acid because it's on the product side, which is coming from a base. And if this one is a base, then definitely the substance added to it is an acid. Now let's move on. And now this is a different kind of question where they are asking you to identify the one that is not a conjugate acid-base pair. Now, to be a conjugate acid-base pair, the difference between the two species must be 1 H plus difference between the two given species, like HA, A minus. This is a conjugate. So it's not a conjugate when the difference is not 1 H plus. So let's look at this one. I have here 4 hydrogens and 3. This is a conjugate acid base pair. This one over here, I have H over here and there's nothing over here. So this is again a conjugate acid base pair. Now look at this one. I have 3 hydrogens and here I have 1 hydrogen. So the difference is more than 1 H plus between them. It means that this is not a conjugate acid-base pair. To be a conjugate acid-base pair, it must be like that H2O with H3O plus or H2O with OH minus. So like this, the difference is 1, 2, and 3. That's 1 hydrogen difference. And here I have 2, and then I have 1. This is 1 hydrogen H plus ion difference. Moving on with the question. Which of the following statement are true for HCOOH? Now here, this is an acid, and this is the one that can be donated. If the formula is complicated for you, you can simply replace this part with HA. Now, this is a weak acid because the list of strong acid, you have to come to the exam knowing it. They're HCl, HBr, HI, HClO4, perchloric acid, HNO3, nitric acid, and sulfuric acid. This is the most known list of strong acids. So this one is definitely a weak acid because it's not part of this list. Now, is it a triprotic? A triprotic, it must have 3 protons in it, and this one has only 1. So no, that's not a triprotic acid. Now, is it a hydrohalic acid? A hydrohalic acid, these are the hydrohalic acid. It means they contain a halogen atom like Cl, group 17, or Br, or I. These are hydrohalic acids. I also have HF, which is a weak hydrohalic acid. So that's not the case. what we have here is an organic acid. Now, yes, it is an organic acid because of the group COOH, which is like this. That's the carbon, that's the first O, that's the OH over here, and here's the H. So this is an organic acid. We have another well-known organic acid, which is the acetic acid, CH3COOH. So the correct answer is 1 and 4, and that is B. Identify the weak diprotic acids. Now, we have diprotic acid. It means it must contain 2 hydrogens and it must be weak. We know for the fact that H2SO4 is a strong diprotic acid. Now, this is a strong monoprotic acid having 1 hydrogen in it. This is a weak triprotic acid having 3 hydrogens in it. This is a strong monoprotic, and this one is a weak diprotic acid because it has 2, and that is not H2SO4. So this is weak acid. It's not the list. It's not part of the list of strong acids. Of the following acids is a strong acid. So they want us to choose the strong acid. Now this is a strong base. This is a weak diprotic acid. That's a strong monoprotic oxyacid, and that's a weak monoprotic acid. So the strong acid here is this one. So as I mentioned here, you need to know the list of strong acids. And I am also going to mention here the list of strong bases that you need to know for the exam. So from group 1, the list of group 1 metals, we have LiOH, NaOH, potassium hydroxide, cesium hydroxide, rubidium hydroxide. These are the strong bases. Now from group 2, beryllium hydroxide is a weak base. Magnesium hydroxide is a weak base, but calcium hydroxide and barium hydroxide and strontium hydroxide are all strong bases. So again, let me put here the list of strong acids that you need to know: hydrochloric acid, hydrobromic acid, hydroiodic acid, and I have nitric acid, sulfuric acid, perchloric and perchloric acid. Okay, so basically these are the most famous list of strong acids and bases. Whatever that they give you that it's not part of these 2 lists, it means that they are giving you a weak acid or a weak base. Like for example, HCN is not part of this list. That's a weak acid. HF, that's a weak acid. Ammonia, that's a weak base. Let's move on. Of the following is a weak acid. So I said that HNO3 is the strong acid. So that is a weak acid. That is a strong base. That is another strong base, and that is another strong acid. So the correct answer is A. Describe strong and weak acids. What's the difference between them? So I'm not going to mention again the strong acids, but what's the difference between them? Strong acids are species that fully ionize in water. It means when I have HCl, HCl is gonna fully ionize. It's a one direction arrow, and it's gonna give me H plus and Cl minus. They form strong electrolytes, so they form strong electrolytes, and I mean by this that they are strong and good conductors of electricity, strong electrolytes, and their Ka, their ionization Ka is very large. Now for the weak acids are species that partially ionize. So weak acids are species that does not completely ionize, they partially ionize in water, in solutions in water. So if I have an example, HF, that's the kind of arrow that I am going to use to indicate that HF doesn't completely go to H plus and F minus. Majority of the molecules of the HF remain unionized, and we only get some small quantity of H plus and F minus. And because weak acids, they partially ionize or dissociate into ions, they form weak electrolytes, meaning that they are weak conductors of electricity. Which equation represents the ionization of hydrobromic acid? Hydrobromic acid, that's HBr, and not HBrO4. This is perbromic acid. Just like HClO4, this is perchloric acid, and HBrO4 is perbromic acid. Now this ionization is correct in terms of an ionization, but that's not the ionization of hydrobromic acid. Hydrobromic acid ionizes in this way, and why I chose it also because it's a one-side arrow. This could be also written like this: HBr plus H2O, one-side arrow, giving H3O plus, being this one a donor, and Br minus. Of course, when you write an equation, you always have to put the physical states. So in this one, also, the physical states, if they are present, they must be AQ, AQ, AQ. It means that this ionizes, or you can also use the word dissociate in water. Now, what's the difference between a strong and a weak acid? So this is again another question repeated. A strong acid fully, completely dissociates or dissociates, or I can also say ionize. It means it forms ions in water to form H plus and the anion conjugate. Like if I have HA, it's gonna give me H plus and A minus. I call it anion. Whereas a weak acid is going to partially, incompletely, like it's not a full ionization or dissociation in water. So it dissociates partially in water, but again I get H plus and A minus. However, the quantity of H plus obtained from a weak acid is a lot less than the concentration or the quantity of H plus obtained from a strong acid. Determine the position of the equilibrium and the type of arrow used in dissociation equations of strong and weak. So again, I am going to write an ionization if I have a strong acid. When I write one direction arrow, it means this HA, it's fully ionized into A minus and H plus. So that's the A. I'm just gonna use it like this as a color. And that's the H plus. I don't have any more HA, no more unionized HA. But if HA was a weak acid, it's going to be like this. And intentionally, I'm doing this arrow to the right, to the left side longer. It means, I mean by this that majority of the molecules of HA remained unionized. Like here in the strong, when this equation finishes, I don't have HA anymore. It finished, it's zero. But with the partial or with the weak acid, when it ionizes, I don't have a lot of A minus and H plus. So it's just very few ions are obtained. The majority of the molecules remain unionized. That's why we say that the direction of the equilibrium lies to the left side, toward the unionized acid. And that's one of the reasons why we use this two-sided arrow, just to say that we still have of HA. Which of the following equations represent the ionization of perchloric? Perchloric, just like I mentioned, it's HClO4, and that's a strong acid. So that's hydrochloric acid. This is a wrong ionization for a hydrochloric acid. This is perchloric acid, but that's the wrong ionization because they are saying that this perchloric acid is weak while it's a strong acid. So that's the correct answer. Which of the following is true about nitric acid? You need to know the formula and the name. That's nitric acid. No, it's not a diprotic acid. It is a monoprotic acid. Yes, it is a strong acid, and when it ionizes completely in water. So the correct answer is second and the third, it is D. Which of the following statement is true? A strong acid is composed of a proton only. No, a strong acid is composed of a proton, H plus, with an anion, A minus. So when we put them together, the plus and minus, they cancel each other. I don't have to write it in the formula. So that's wrong. A weak base is composed of a cation only. A weak base, like for example, I can take aluminium hydroxide. That's a weak base. Al3 plus is the cation. So it's wrong. It's not only composed of a cation, it has also in it OH minus the hydroxide ions. A strong acid has a strong conjugate base. That's definitely wrong. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. So when I have a strong acid, HCl, when it ionizes, it's going to give me the conjugate Cl minus. Cl minus is so weak base that later on we're going to call it a pH neutral substance. The conjugate base of a weak acid is stronger than the conjugate base of a strong acid. Yes, so I'm going to write it here. A strong acid gives a weak conjugate base, but a weak acid will give me a strong conjugate base. So they are inversely proportional. The stronger the acid, then which of the following is true? So as I mentioned, the stronger the acid, the weaker the conjugate base. Which of the following will have the strongest conjugate base? Before I read the choices, the one that must have a strong conjugate base must be the weakest acid. So I'm gonna look at this list and choose the weakest acid. That's a strong acid. That's another strong acid. And again, another strong acid. So the only weak acid is HCN, which has a very strong conjugate base CN minus. What does the below diagram represent? This is the auto-ionization of water, because as you can see here, I have H2O molecule added to another H2O molecule. So this is when water ionizes itself. So we call it auto-ionization. How do I know? I am just looking at this one, donated this H plus over here. So this became just OH minus hydroxide ion, and this one became hydronium ion. So we call this an auto-ionization of water. Now we have another one, an auto-ionization for the ammonia. I'm going to write it over here, NH3. I'll write it in this way. NH3, when it auto-ionizes itself, one of them will act as an acid, one will act as a base. So let's say that this is the donor. I'm gonna get NH2 negative. This one became NH2 negative, and the other one became NH4 plus. So whenever this equation is given to you, this is called the auto-ionization of ammonia. So what does the below, what does the below diagram represent? This is ammonia plus another ammonia. One is giving a proton to the other one. So that is the auto-ionization of ammonia. Now, next, define acidic anhydride, basic anhydride. During this term, we studied about metal oxides and non-metal oxides. And I'm going to give examples. Metal oxide like calcium oxide, sodium oxide, magnesium oxide. So these are metal oxides. These metal oxides, when we put them in water, when they react with water, they form bases. So when they react with water, they form a base. So that's why a metal oxide, we call it a basic anhydride. So I'm going to write over here, a basic anhydride is a metal oxide, like for example, beryllium oxide, magnesium oxide, calcium oxide, lithium oxide, etc. These metal oxide, when they react with water, upon reacting with water, we get a base. We get a basic solution. And I'm going to show you. So if I have CaO plus H2O, I'm going to get calcium hydroxide. I'll get calcium hydroxide plus some hydrogen gas will be released. What I care about is that I get a basic solution. Now, for the non-metal oxides. Non-metal oxides like, for example, carbon dioxide, nitrogen dioxide, sulfur trioxide, for example, any non-metal with oxide. The non-metal with the oxide, when they react with water, they will give me an acid. So, is a non-metal oxide that gives an acid in water. So I'm gonna give you an example. SO3 plus H2O, I'm gonna get H2SO4. That's sulfuric acid. I'm gonna give you another example. Here, the SO2, I'm gonna add water to it, so I'll get H2CO3, carbonic acid. I'm gonna add water to it, and I'm gonna get nitric acid. I'm gonna add water to it, and I'm gonna get sulfuric acid. So this is how it works. Define Kw and write the equilibrium expression for the dissociation of water. And this Kw, we memorize its value only at 25 degrees Celsius. Kw, K represents a product constant, and W represents water. So this is the equilibrium constant for the dissociation of water. That's what it calls. Kw is, if I write the equation of H2O ionizing into H3O plus and OH minus, or if you write H2O ionizing into H plus and OH minus, this is liquid. This is liquid. So when I write the expression of Kw, I do not include the concentration of water. So it's simply H3O plus concentration minus OH minus times, So it is H3O plus concentration multiplied by the concentration of OH minus. Or I can say Kw is H plus multiplied by OH minus. Now, only at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the power negative 14. And Kw has no unit. Moving on. Which of the following statements regarding Kw is false? Kw, the value of Kw is always 1.0 times 10 to the power negative 14. That is a wrong statement. It is only, they have to mention, only when temperature is 25 degrees Celsius, because Kw could be different if the temperature was not 25 degrees Celsius. Now, pKw is the logarithmic function of Kw, and that is 14. Yeah, but here they saved this answer by saying at 25 degrees Celsius. So pKw is equal to 14 at 25 degrees Celsius. So the only reason that I did not choose D, it's because the sentence is missing. They must say that it is equal to 1.0 at times 10 to the power negative 14, but they have to mention which temperature. Kw is changes, yes, definitely, it changes with the temperature. Sorry, here we need to choose the false. So that is correct, that is correct. The Kw shows that water is a weak acid. Actually, I think there's something incomplete in this question because this sentence is wrong. I thought that D is wrong. I would say that D is incomplete. To be a correct statement, they must mention in the question that it is 25 at this value at 25 degrees Celsius. Now given C, the value of Kw shows that water is a weak acid. Actually, in this case, water is a weak acid and a weak base. So if you look at this ionization or autoionization that I was just talking about, water here is acting as an acid and it's acting as a base. That's why we call it an amphoteric. So that's a weak acid along with a weak base. So I think here we spotted a mistake in this here. So there are C is the one that is wrong and not D. But D, the sentence is missing. They must mention at 25 degrees Celsius. So let's continue. The molar concentration of hydronium ion. Whose hydronium ion? That's H3O plus. In pure water. And see, they told you it's at 25 degrees Celsius. When they say pure water, it means when neutral. And when neutral, pH equals 7. Or I'm talking about this temperature. Also, we know that OH minus is equal to H3O plus. So, if I substitute in Kw, H3O plus multiplied by OH minus. Now, let's substitute OH minus and put instead of it H3O plus squared, and that is 1.0 times 10 to the power negative 14. So square root of Kw will give me the value of the hydronium ion concentration, which is 1.0 times 10 to the power negative 7 molar. The molar concentration again of hydroxide ion in pure water, since I mentioned here that they are equal, so OH minus also is 1.0 times 10 to the power negative 7. Moving on, what is the relationship between H plus and OH minus in a neutral solution? As long as they don't mention in the question the temperature, only say that in neutral solutions, H plus and OH minus are equal. Do not mention they are equal to 1.0 times 10 to the power negative 7 because they did not tell you at 25 degrees Celsius. Now here, calculate H plus and OH minus in pure water at 25 degrees Celsius. They have to mention this because if they don't, I won't be able to use the value of Kw, which is 1.0 times 10 to the power negative 14. So calculate the concentration of H plus when OH minus is 0.10. So to calculate OH minus, we use the formula of Kw, H plus times OH minus. So it is Kw over H3O plus, and that is 1.0 times 10 to the power negative 14. Sorry, I did the opposite. Here they are asking for H plus or H3O plus. It's the same. So here, OH minus 0.10. And the answer is going to be 1.0 times 10 to the power negative 12. Or I can give it to you in a different way. 1.0 times 10 to the power negative 14 is H plus multiplied by the value of OH minus, and you solve for X on the calculator. A solution has now H plus is 6.0 times 10 to the power negative 5. Find the OH minus of this solution. So again, Kw equals to H plus multiplied by OH minus. So 1.0 times 10 to the power negative 14 is 6.0 times 10 to the power negative 5 and OH minus. Solving for this one, we find OH minus to be 1.7 times 10 to the power negative 10 molar. Let me just double check it. So 1.0 times 10 negative 14 over 6.0 times 10 negative 5. So yes, that is correct. Describe the pH range for acidic, basic, and a neutral solution. In your description, you must mention, if you want to give values, at 25 degrees Celsius, pH below 7 is acidic, pH above 7 is basic, pH equal 7, we have neutral solution. Neutral solution. Now, just like KW, we have, just like pH, we have another scale, which is the POH. Anytime you add pH and POH, it's going to be equal to 14 at 25 degrees Celsius. They are inversely proportional, by the way. Define pKa and write the mathematical formula needed to calculate it. pKa is a logarithmic function related to the Ka, the dissociation constant. So I mentioned previously that if Ka is a small value, pKa will be large value, and vice versa. Now, pKa is equal to minus log Ka. Again, pKb is equal to minus log Kb. Now, you need to know that if I multiply Ka by Kb, I'll get again Kw. And if I add pKa plus pKb, I'll get pKw, which is equal to 14. And this one is equal to 1.0 times 10 to the power negative 14 if the temperature is 25 degrees Celsius. Also, I have pH plus POH, that is equal to 14. So all of these formulas are related together. So pKa, it measures the strength of the acid, and it will show me how easily or how easily the acids donate its proton. So again, if Ka is a large value, it means I have a weak acid. If Ka is a very small value, it means I have a strong acid. Now, same thing we're going to do for pKb. pKb is the logarithmic function, but this time it is related to Kb. So it's the logarithm of the base dissociation constant Kb. The larger the Kb value, the smaller the pKb. What does that mean? The larger value of Kb. So if I have the stronger the base, it will have a larger pKb. The smaller the pKb. So pKb is minus log Kb. You don't have to memorize these formulas because they are most of the time given in your formula sheet. Now, if Kb is 1 times 10 to the power negative 4, what would be pKb? So again, I'm going to use the logarithmic function 1 times 10 to the power negative 4, and that is equal to 4. A solution has a pH of 7.51. What is H plus and what is OH minus? So I'm gonna explain it in a simple way. Having pH, I can find pOH because pH plus pOH equal 14. So pOH would be 14 minus 7.51, and that is 6.49. Now, look what I'm gonna do to find H plus from pH and to find OH minus from pOH. pH is minus log H plus. So I'm gonna put 7.51 minus log H plus, and I'm gonna plug it into my calculator and solve for H plus. So H plus concentration here is going to be 3.1 times 10 to the power negative 8 molar. Don't forget the unit. pOH, on the other hand, is equal to minus log OH minus. So 6.49 minus log OH minus, plugging it into my calculator, I get the concentration of hydroxide ion to be 3.2 times 10 to the power negative 7 molar. A solution has OH minus 6.2 times 10 to the power negative 5. So first of all, we're going to start with the pOH. pOH is equal to minus log OH minus. Minus log 6.2 times 10 to the power negative 5. Therefore, pOH is 4.21. Now using this formula, pH plus pOH equal 14, I can now calculate pH and say it is equal to 14 minus 4.21, and the pH is 9.79. pH and pOH has no unit. Moving on. The Ka, I think here we reach the ICE table. The Ka value of hydrocyanic acid is 6.2 times 10 to the power negative 10. What is the pH of a 0.750 HCN? You have to be very careful in these kind of questions. You must write the dissociation equation and the ICE table to earn the full mark. So let's begin. HCN plus water molecule. It is weak, be careful. They will never give you Ka if you have a strong acid. So by simply giving Ka in this question, it means that this is a weak acid. Therefore, I must write these two-sided arrows. It will ionize to give me hydronium ion and cyanide anion. Now, initially, change and equilibrium. We are not going to write anything underwater because it is liquid. It doesn't participate and becomes an ion over here. So, initially, this is the given concentration of hydrocyanic acid. We don't have yet hydronium and cyanide ion because they did not form yet. This is initially. Now, when HCN is going to ionize, some part of it will be ionized, will be lost because it is going to give me H3O plus and Cn minus. So when we reach equilibrium, the concentration of HCN remaining is the initial concentration minus the portion that ionized. Now, when we write the formula of Ka, it is the concentration of H3O plus multiplied by Cn minus over HCN. Now I'm going to substitute the value of Ka, and you have to look here. The value of Ka is very small. It means that only a small portion of this HCN is going to ionize. So x, when we calculate the value of x, it's going to be a very small value. So that is x times x, so that is x squared over 0.75 minus x. Now we're gonna do here a small assumption and ignore this x. So we're gonna assume that x is small. Actually, this, we're gonna say that x is small, so Ka, or 6.2 times 10 to the power negative 10 is approximately equal to x squared over 0.75. And I can prove this to you. If I divide the given concentration, which is 0.75, over the Ka value, I am going to get a number that is a lot more than 500. Only when this answer here is less than 500, you cannot do this assumption. But as long as you get a very large number, you can cancel this x. Now, solving for x, we find it equal to 2.0 times 10 to the power negative 5 molar. See, it's very small. Now, who's x? X is H3O plus and x is Cn minus. And I am interested in H3O plus because the question wants me to get pH. So I'm gonna say x is equal to the concentration of H3O plus 2.0 times 10 to the negative 5. Now we can calculate pH minus log H plus. And the answer is 4.667. Now let's continue. When you get this question and a multiple choice question, you don't have to do the ICE table. There is a fast way to calculate the pH. Okay, so here they want the pH of a given concentration of a weak acid, benzoic acid, and we have the Ka. So x, which is H plus, it is equal to square root of Ka times the original concentration. You just take it from here. After ignoring this x over here, the Ka multiplied by the concentration is equal to x squared. So there is a fast formula that I can use only in multiple choice questions because I don't have to show my work. So in this case, it is a square root of 6.3 times 10 to the power negative 5 multiplied by the given concentration. Now, upon doing this, I get H plus, but I need to find pH. So pH is minus log this value. And that is equal to 2.3. Here again, another question. They are asking me to calculate, this time, the Ka of formic acid. But they gave me the pH that is equal to 2.38. I'm just gonna do the same step of a weak acid, and I must start by writing the ionization equation. To earn the full mark, you need to write the ionization equation, and you need to show the ICE table. So it is HCOO minus and H3O plus. This is initially, change, and equilibrium. So we have 0.10 initially. We don't have yet HCO minus and H3O. We're not going to write anything under H2O. So I have here minus x, plus x, and plus x. This is 0.10 minus x, x, and x. Now Ka is equal to HCOO minus times H3O plus and HCOOH. Now, now I need to find this Ka. Now from the value of pH, because pH is given here to me, I can find this x. pH is equal to minus log H3O plus. Now having the pH to be equal to 2.38, I can calculate H3O plus. And H3O plus is going to be equal to 4.2 times 10 to the power negative 3. And H3O plus is x. So now I am going to substitute for the value of x. Zero 0.10 minus 4.2 times 10 to the power negative 3. And the value of Ka is going to be 1.8 times 10 to the power negative 3. Again, no unit for Ka. Now, moving on. Calculate the percentage of the acid that is ionized in question 40 in the previous question. Now, the percent of ionization, that's a formula. Most probably is not given. You need to memorize it. It is equal to x to the H plus at equilibrium over the initial concentration of the acid given to you multiplied by 100 because it's a percentage. So from the previous question, we know that x is equal to 4.2 times 10 to the power negative 3, and the given initial concentration is equal to 0.10. So here, that's the one. So I'm going to write over here percent ionization is equal to x over c multiplied by 100. So it is 4.2 times 10 to the power negative 3 over the given concentration in the question of the acid, and that is 4.2%. That is a weak acid because the ionization is less than 5%. Always, whenever the ionization is less than 5%, we can ignore this X because it's a weak acid. 0.110 solution of a weak acid has a pH of 2.84. It is a weak acid, but I do have the pH, so I can simply use the pH to get the H plus and ignore the given concentration because pH is given to me. So pH is minus log H plus, so 2.84 minus log H plus, and we get H plus to be equal to 1.4 times 10 to the power negative 3 molar. Underline the value of Ka for the acid in question 42. The value of the weak acid is 1.8 times 10 negative 5 or 1.0 times 10 to the power negative 1. Now, having the H plus, I'm going to give you again the formula. Ka is x squared over c. So x squared is the H plus. So 1.4 times 10 to the power negative 3 squared over the given concentration. So if we plug this into our calculator, we get the value to be 1.8 times 10 to the power negative 5. With our video tutorial, we reach subtopic 1.4. Write the type of the base below. And they mean by write the type to identify whether the base is strong or weak. So whenever you see the metal of group 1, lithium, potassium, sodium, rubidium, cesium, and the metals of group 2 like calcium, barium, strontium, strontium, these they form strong bases. The rest, they are weak bases. So this is a strong base and the rest are weak. All the bases of ammonia are weak. So let's continue. A solution contains 1.0 times 10 to the power negative 5 sodium hydroxide. That is a strong base. What is the pH and the pOH of the solution? Now, since we know that a strong base fully ionizes in water, we are going to get Na plus NOH minus. And that means that all the NaOH minus that we have over here are going to fully turn into OH minus. So I can use the concentration, or I can say that the concentration of the given base totally turned into OH minus. So the concentration of OH minus is now 1.0 times 10 to the power negative 5. Having OH minus, we can calculate the pOH to be minus log OH minus, which is 5. And using this formula, pH plus pOH equal 14, I can say pH equal 14 minus 5, and that is equal to 9. Moving on, write the statement below. Write if the statement below is true or false. In the Kb expression, water is included in the equilibrium constant expression. They are telling me that in Kb expression, I include water, and that is wrong. Because in Kb expression, here we put the base, we put hydroxide ion. Down in the denominator, we put the given base. And up here, we put the conjugate acid of this base. So no H2 is not included. So that is false. The Kb expression for weak base dissociation reaction includes the concentration of conjugate acid only. That is not true. I just wrote the formula. The value of Kb indicates the strength of a base. That is correct, because it will give me an idea if the base that I have is weak or strong, or if it's weaker or stronger than another given base. Now, define acid salt and identify its type, acidic, basic, or neutral. So list an example of an acidic, basic, and neutral salt. Before I do this, I'm going to give you a list of ions to remember. If these ions were present in the given salt, you can say that they are pH neutral or acidic or basic. So I'm going to give the list of positive ions. So I'm going to start lithium, sodium, potassium, rubidium, cesium, calcium, barium, and strontium. If you see this list of ions, you call them pH neutral, and all other positive ions, whenever you have them in the formula, they are acidic. Now, the list of negative ions, and I am talking about the conjugates, the anions that are coming with strong acids, and that is Cl minus, Br minus, I minus. I also have SO4 2 minus, nitrate, and perchlorate. These ions, whenever you see them in the part of the formula of the salt, you'll say that they are pH neutral, and the rest all the rest of negative ions are basic. Now let me show you how I'm going to give examples of acidic, basic, and neutral salt. So let's say I have an NaCl is given down, so I'm gonna give KCN. Now K, I mentioned it in the list, that is pH neutral. Now Cn negative, that's a negative ion that is not part of this list of negatives, so it means that this is a basic ion. So therefore, this given salt is basic. Next, let's give another one. What if I have magnesium chloride? So magnesium is a positive ion that is not part of this list. So magnesium is a positive ion that is acidic. And the chloride is part of this list. So chloride is pH neutral. So this salt is acidic salt. Now, when do I have a neutral salt? Whenever I have a combination from this list of positive ions with something from these negative ions. So I'm going to give you an example. KBr, neutral. CsClO4, neutral salt, and etc. If you find this hard, check my tutorial video about salts on my channel. What is the type of NaCl? So Na is pH neutral, Na plus, pH neutral, and Cl is also pH neutral. Therefore, this salt is overall neutral. Now, again, I'm just going to mention that these ions, we call them pH neutral because they cannot hydrolyze with water. It means they cannot react with water to become acidic or basic. So that's why they remain neutral. Another question, calculate the Kb and the pKb of the butyrate ion. Here's the formula. And the pKa of butyric acid is 4.83. So here I have the pKa, it is given to me. pKa is 4.83. Now, directly from the pKa, I can calculate the pKb by using the formula of pKb plus pKa equal 14. So pKb plus 4.83 equal 14. pKb is equal to 9.17. Now, from the pKa, I can use this formula, minus log Ka. And from the pKb, I can use minus log Kb. So let's substitute. I'm going to use this space over here. So pKa, which is 4.83, equal minus log Ka. And we're going to solve to find that Ka. Here they didn't ask for Ka, so I don't have to do this step. They just ask for Kb. So I am going to substitute for pKb, that is 9.17 minus log Kb, and Kb is going to be equal to 6.8 times 10 to the power negative 10. I also could have used a different formula and found Ka first from the given pKa, and then use the formula of Ka times Kb equal 1.0 times 10 to the power negative 14 to calculate the Kb. So these formulas are given to you, but still keep them in mind. pKa is minus log Ka, pKb is minus log Kb, pKa plus pKb, that is 14, Ka times Kb, that is 1.0 times 10 to the power negative 14. I'm always talking about 25 degrees Celsius. I have to mention this. On the other hand, I'm just gonna remind you, pH is minus log H plus, pOH is minus log OH minus, pH plus pOH is 14, and H plus multiplied by OH minus is 1.0 times 10 to the power negative 14, only at 25 degrees Celsius. You have to mention this. Let's continue. Writing the dissociation equations of polyprotic acids. This could be challenging, so you have to be careful in writing the equation. So if this is diprotic acid, it means I have 2 steps of dissociation equation. So we start 1 H plus at a time. H2C2O4, don't forget to put the physical states, plus H2O liquid, and this is not one of the list of strong acids, so I'm going to use the reversible sign arrows, H3O plus, and I'm just going to omit 1 H from those. So it's going to remain 1 H, 1 H plus 1 H C2O4. I'm going to write it again. Okay, it didn't save. So H2 C2O4 again, plus H2O liquid. I'll get HC2O4 minus, because you removed 1 H plus H3O plus. That's the first step, dissociation. Now the second step, you take this one conjugate base formed, and you dissociate it again, plus water, and you get, now you remove this hydrogen, C2O4, and now it becomes 2 minus instead of 1 minus. That's AQ, plus H3O plus AQ. So again, that's a diprotic acid, so 2 steps ionization. Now if I have a triprotic acid, it means 3 steps of ionization. So that's water, that's the first step. So 1 H at a time. I have H2 remaining, that's 1 minus, plus H3O plus. Now again, I'm going to take this one and do another dissociation. H2PO4 minus, that's the second step of ionization. Now 1 hydrogen remains, but now it is 2 minus, plus H3O plus. And now the third step is to get rid of the third H in it. So we're gonna do another ionization. We get PO4 3 minus and H3O plus AQ. Place the following in order of increasing acid strength. We notice here that all of these formulas, they start with HClO. Now, the number of oxygen in the formula is the one changing. So the more oxygen you have in the acid, the more the bond becomes weak and the acid becomes stronger. It means that is the weakest because it has 1 oxygen, and that's a bit more stronger because it has more oxygen in it, and this one is stronger, and this is the strongest. Having 4 oxygen in it, it's gonna make the bond between the H and the ClO4 very weak bond, which means it's easily broken and this acid will easily donate the H plus, and that's what makes it a strong acid. Define Lewis acid and base. Lewis acid, here in Lewis we talk about electron pair acceptor and electron pair donor. So a Lewis acid is an electron pair acceptor. Usually these are the atoms in the molecule or in the compound that did not complete their octet rule, or the positive ions because they lost their electrons, so now they can accept electrons. And Lewis base are the ones that are electron pair donor. So any molecule that has lone pairs on it or negative ion is a Lewis base. So let's look at this one. Let's look at the adduct formed over here molecule. We see that this OH had here 3 lone pairs. One of them is gone. It means that this is the donor. Now it donated it to the carbon because it's attached to the carbon. And now carbon is going to have, as a result of this additional electron lone pair that was given to C, now C has a negative charge. So that is an electron donor. That's a base, Lewis base. And that's an electron acceptor. It means that's a Lewis acid. If you forgot or you're confused, just by looking at OH minus, you already know that this is a base. So you're not going to call it a Lewis acid. It is still a base. Let's continue. Reaching the topic 2. Label the given graph. So, any curve given to you, you have to check from where it is starting. This curve, it's starting from below. So this is the titration of an acid with a strong base. Now I left a space. What is this? Is it a strong acid or a weak acid? By looking at the point here in the middle of the curve, this point is called the equivalence point. At the equivalence point, if pH is 7, it means that I am titrating a strong acid with a strong base. Another indication, the curve starts from below 2 and it's almost a straight line increasing slowly. So this indicates that this is a strong acid. Now this point is the initial pH of the acid being titrated. So this is the initial pH of acid being titrated. Now this is when H3O plus is still in excess, we are still in acidic medium, we did not reach the equivalence point. So this is the area before the equivalence point when H3O plus is in excess. Now here, this is the point after the equivalence point, and that is where OH minus, because I am adding a base, becomes in excess. Now I need to mention that only at equivalence point I have the OH minus equal the moles of H plus. Now here's another graph of a weak acid with a strong base. So the weak acid from a strong base, I can immediately recognize it by looking at the pH at the equivalence point. If the pH is not 7, it means that I have a weak substance titrated with another strong substance. Now, since this curve starts from below, it means that I have a weak acid titrated with a strong base. So the pH at equivalence point must be above 7, and indeed it is 8. This is the volume at equivalence point. Now this is the point after equivalence point when OH minus becomes in excess. Here H plus and OH minus are equal. And we also have what's giving this basic medium is the presence of the conjugate base of that weak acid at that equivalence point. Now, there is a very important region in the titration of a weak acid with a strong base, which is called a buffer region. And at this point, this is the buffer range. This is where I have a weak acid and I have its own conjugate base, and they constitute a buffer solution. Now, only at half equivalence point, which basically at 12.5 in this one, we can identify the pH that is equal to pKa. Now, this point here is the initial pH of the weak acid just before the titration. Now, which one of the following pairs cannot be mixed together to form a buffer solution? Now, to form a buffer solution, I can mix a weak acid with its own conjugate base, or a weak base with its own conjugate acid, or I can mix a strong acid with a weak base, but the weak base has to be a lot more, or a strong base with a weak acid, and the weak acid has to be more than the strong base used. So let's see where can we find the buffer in this list given to you. So here I have HO and H2 and HO and H3Cl. So 2 and 3, that's a base, and that its own conjugate base. I know it because I have one more hydrogen. So that's a buffer. This is a salt, a neutral salt, and this is a strong acid. That is not a buffer. That is F minus, and that is HF, conjugate base and its own acid. That is a buffer. And also this one, NO2 and HNO2, that is a buffer. To recognize the buffer immediately, just look for one hydrogen missing in one of the formula, only one. So again, which one cannot form a buffer? So 3, 4. This is a base with its own conjugate base plus its own conjugate acid. So that is a buffer. This is a strong acid with a weak base. So yes, that is a buffer. This is a strong acid with a strong base. No, I cannot. That's not a buffer. This is not how we form a buffer. There's one H, there's an H missing. This is a buffer. So the correct answer is C. Again, which of the following is a buffer? So let's look at it. HI, one hydrogen difference, that is a buffer. Oh, wait. Wait. No. I'm sorry. That's not a buffer, and I'll tell you why. Because the conjugates with the acid must be a weak acid, and that is a strong acid. And a neutral, a base is here. That's a neutral salt. That's not a buffer. That's a strong acid over here again. And that's a neutral, that's a neutral salt. That's not a buffer. That's a strong acid, neutral salt. That's a weak acid. And that's a basic salt, HFF. So that is a buffer. Let's move on. What change will be caused by addition of a small amount of HCl to an acidic buffer solution containing a weak acid and its own conjugate base? If I have a buffer and I add a strong acid to it, the buffer will resist the change in pH. However, it's going to decrease slightly, but still it will resist the change in pH. Now, since the addition is acid to the buffer, and a buffer is made of an acid with its own conjugate base, so upon adding an acid, the conjugate base is going to react with this acid to neutralize it and decrease its effect. If a base is added, like for example NaOH, in this case, the acidic part of the buffer will react with this NaOH to neutralize it and decrease its effect on the pH. So therefore, here, by reading the sentences, we find that the concentration of the conjugate base, yes, it's going to decrease because it's going to be consumed since it's going to react with the added HCl. And the concentration of the weak acid is going to increase. True or false? We're almost done. So, true or false? An effective buffer has a ratio base over acid in the range of 1 to 10, not 10 to 100. So that is false. A buffer is most resistant to pH when the acid and the conjugate base are equal. That's the most effective point of a buffer. It's at its maximum capacity. A buffer cannot be destroyed by adding too much strong base. Definitely a buffer can be destroyed if we too much added strong acid or strong base, because the added strong acid or strong base are going to consume the acid or the conjugate, the weak acid or the conjugates of the buffer. And they're going to react with that added strong base to neutralize it. So we're consuming it. So definitely there's an end to the buffer if you added too much of a strong acid or too much of a strong base. Define a buffer solution. A buffer solution is a solution that resists the change in pH upon the addition of a small, and I insist on mentioning small in your answer, a small amount of a strong acid or a strong base to it. Why small? Because if you add a large amount of a strong acid or a strong base, you are going to destroy that buffer. Give an example of an acidic and basic buffer. The best example, for example, of an acidic buffer, I can say HF mixed with NaF, HCN mixed with LiCN. Just keep the simple ones. Basic buffer, ammonia with ammonium chloride, for example. So that is a basic buffer. The statement. In a buffer solution, when the concentration of a weak acid and its conjugate base are equal. This information is very important. When the weak acid and the conjugate base are equal, at this point, the pH is equal to the pKa. And I'm going to explain why. If we look at the Henderson-Hazel-Balch equation, pH equal pKa plus log the conjugate base over the acid. So if these two concentrations are equal, it means we are dealing with log 1. So pH equal pKa plus log 1. And log 1 equal to 0. That is why the pH equal to pKa. And we only have this at half equivalence point. The Henderson-Haselbalch equation, like I said in the previous question, it is pH plus pKa log base over the acid. Like for example, if I have HF, you are going to write HF down, and up you are going to write the conjugate F minus. There is another version for the Henderson-Haselbalch equation for POH. If you want, I can write it over here, but we can still use the first one as well. So it's pKb plus log the base over the conjugate acid. Or I'm just going to write it in words. It's the base down and the conjugate acid up. Now, let's continue. What is the pH of a solution prepared by dissolving 0.150 mole of acetic acid? That's the acid, HA, and 0.30 mole of sodium acetate. You have to be careful to what you are reading. The acid and its conjugate base, their name, they're so close and similar. Acetic acid, acetate. We don't need the sodium in this. So the acetate, I'm gonna write the formula as A minus. I don't have to know the formula in order to solve and find the pH. And insufficient of 1 liter. Note that here in the Haselbalch-Henderson equation, you can use concentrations and you can use mole. So I don't have to find the concentration. If it's not given to me, I can simply use the mole, because if I'm gonna divide, I'm gonna divide by 1, so it's basically the volume will be cancelled on the ratio. So pH equal pKa, but I don't have pKa, so I'm gonna use the formula of minus log Ka, which is 1.8 times 10 to the power negative 5. Previously, I mentioned that pKa is equal to minus log Ka. So that's why, since I don't have pKa in this formula, I am applying this formula down in here. Since I don't have the pKa, so I'm going to write minus log plus log of the base over the acid. Okay, so the result is going to be 5.56. That's the pH. What is the effective pH range of a buffer relative to the pKa of the weak acid? Now, we always say that the best buffer is when you get the acid and its own conjugate base concentrations very close and similar to each other, but up to certain limits. So if we look at this formula, pH equal pKa plus log the conjugate base over the acid, it's in the ratio. You know, these concentrations, the best is when they are equal, and the least effective, or the range in which the buffer works, is when I have 1/10 ratio or 10/1. So that's the maximum, and that means that pH equal pKa within the range of log 10, which is 1, and within the range of -1. So whenever they give you the pKa of the buffer, so the pKa of the buffer, you take it, and you will say that this is included in between a +1, an interval of +1, and a -1. So if I took the previous question, our pKa that we calculated it in here, 1.8 times 10 to the power negative 5. In our previous question, the pKa given was 4, oops, I wrote kPa, it's pKa, so it is 4.74. So what is the range of this buffer? From the -1 to the +1. 5.74. So this buffer can only work and change pHs between those two values. Beyond those two values, the buffer is not anymore effective. Which solution is an effective buffer? So first, let's look at the solution if it's a buffer or no. That's a strong base, and that's a strong base. That's not a buffer in the first place. That's a neutral salt, and that's another neutral salt. That's a base, and that's its conjugate. There's one H difference. And we look at the concentrations, they're equal. So that's a buffer and a very good one. Moving on. Describe the curves below. I see in this graph several titrations of acids with strong base. That's what I see. Now, for the first one, I first going to locate the 7. So this is pH equals 7. So the first curve, which is this one, corresponds to the titration of a strong acid with a strong base. Why? Because the pH at equivalence point equal 7. And as you can see, the curve starts around 2 and it increases slightly. For the other acids, we are using weak acids. But as you can see, the pH at initial starts increasing. The pH initially, from where the curve started, keeps on increasing whenever you have weak and weaker and weaker, whenever the acid is weak. So these set of curves, they show the strength of an acid. How does it affect the titration curve? So the weaker the acid, the higher the pH at start of the titration curve. That's one. Second, as you can see, the pH at equivalence for the second curve, for this one, the pH at equivalence is probably here, and the other one, maybe I'm over exaggerating, here and more. So the pH at equivalence point, pH at equivalence point increases. It becomes more and more above 7. Increases when the acid being titrated gets weaker, is weaker. Okay, so the weaker the acid, the higher the start of the curve. And as you can see, the jump becomes steeper because the acid is weaker. Now for the pH equal pKa, we always have to take the equivalence point and then half of it, and then determine the pKa. So that's the first pKa, that's probably the second pKa, that's the third, and that's the fourth. For titration of weak acid, strong base, weak acid and strong base, we deal with buffer in these titrations. But when I have a strong acid with a strong base titration, I only have the equivalence point. That's all. But for the weak with a strong, we have what we call half equivalence point obtained at volume at equivalence divided by 2. At that point, the pH equal the pKa. We can get it from the graph, from the titration curve. Let's continue. Which of the following are true at the equivalence point of a titration of a strong acid and a strong base? We don't have half equivalence point. So that's as a start. So pH at equivalence point is equal 7, not greater than 7. At the equivalence point, the number of moles of hydroxide ions are equal to the number of moles of H+. They're not less, they're not higher, they're equal. That's why we call it equivalence point. At the equivalence point, the number of moles of hydroxide ions and hydronium ions are equal. Yes, that's it. What is the concentration of 100 milliliter of acid titrated with 25 milliliter of 0.5 NaOH? So they want us to find the concentration of the acid. We do have the volume of the acid, and at equivalence point, because I just said that N of the acid, mole of the acid is mole of the base, they're equal, so we get to write the formula CAVA equal CBVB. So now, this acid is being titrated with 25 volume milliliter of a base. So CBVB, that's VB, and that's the concentration of the base. So let's substitute. That's 100, 0.5, and 25. So the final answer, the acid titrated will have a concentration of 0.125 molar. Now, for different types of titration, what would be the pH? Let me start with pH equals 7. When I have a titration of strong acid with a strong base, and vice versa, by the way, strong base. I have a pH less than 7 when I am titrating a weak base with a strong acid, and the pH is above 7 when I am titrating a weak acid with a strong base. I didn't say and vice versa in these choices. So I also have pH equals 7 when I am titrating a strong base with a strong acid. Now, finally, here, this is almost the last question. Explain why phenolphthalein is suitable for the titration below. As it must be given when they ask you a question like this, they must ask you they must give you the pKa of phenolphthalein. So phenolphthalein pKa is about 9.3 or 9.4. Okay, now pKa is suitable for the titration of a weak acid. I see here a titration of a weak acid with a strong base. If you look here, here is the pH at equivalence point, and it seems that this phenolphthalein changes the color range at that point. So let's see the range. As I said, -1 and +1. So it's 8.3 to 10.3. That's the range of my phenolphthalein, which falls in the area of the, as you can see it here, it falls in the area of the pH at equivalence point. So this is a suitable one. If the indicator changes color here, for example, which is not in the area of the equivalence point, pH, so it won't be suitable. So to choose the correct indicator, the range of that indicator the pH at equivalence point must be within the range of that indicator. And in the titration of weak acid with a strong base, the pH at equivalence is above 7. So probably maybe it's 8.5 or 9, so it's within the range. Look at it. Here it is 9. And the last question in our focused questions, the graph below shows the titration curve. Okay, sorry. So this one, they're just asking us to describe this curve. As you can see here, I am looking at 3 equivalence point. So I am dealing with a triprotic acid. So this is the titration of a triprotic acid. And by triprotic acid, it means that I have 3 equivalence points. So the volume at first equivalence point is 50. The volume at second equivalence point is this value over here. And the volume of third equivalence point is this one. Now, how do I calculate half equivalence point? So half of 50 is here, so probably that's the pKa1. Now from 50 to 85, this area over here, half of it is here. So this is here pKa2 and this is pKa1. Now to check the equivalence point, the third equivalence point or the third pKa, we take from the second equivalence point to the third equivalence point. So from this equivalence to this equivalence, half of it is probably here, and this is the point where I have pKa3. Now this is pH1 equivalence point. That's the one. That's the one I'm highlighting in red. This is the first pH at equivalence point. This is the second pH at equivalence point. That's the third pH at equivalence point. 3 jumps means I have a triprotic acid. Thank you and good luck.